Hey, Happy New Year. Hope you had a good break. Today we're going to learn about work and power. So the entire first semester was all about mechanics of motion, how things move, and kinematics, and all the math associated with that. This semester is entirely dependent on energy. In order to know energy, you have to know forces, so we're never ever going to let go of forces. So work is literally a force that's applied to an object that causes the object to move. The force must be directed parallel to the direction of whatever the object moves. Work is equal to force times the distance that the object moves. Work is measured in joules, and I know you just giggled because a joule to you is something different, but a joule in physics is a Joule, which is a unit of measurement of energy, and we're going to use it throughout the semester. Force is still measured in newtons. Distance is still measured in meters, but you notice we didn't use x or y for distance this time. We're simply calling it d. This is also on your formula sheet, which is why I've boxed it. You should find this on your formula sheet, so you'll have it for every test and quiz. When a force is directed at an angle, so it's not parallel, we'd have to do the same thing we do for things when they're horizontal. If it's taken with respect to the horizontal, you take cosine of the angle and you multiply it by the force. If it's vertical, like if the angle is taken with respect to the vertical, like it would be on an incline, then this might change, but you're going to have to read those incline questions very, very carefully. So for the most part, as long as the object is moving on a horizontal plane, then work is equal to force times distance that it travels times cosine theta. So for both of these, your force and your distance are considered direct proportions to work. Therefore, if you have more force directed over a distance, you have more work done. If you have more distance that you travel, then more work has to be done to travel that distance, because force and distance are direct proportions to work. So in order for work to occur, you have to have a few things that have to happen. Your force must be applied. You can't just have something that's just sitting there stationary. A force must be applied. It also can't be like a hockey puck. Like if you hit a hockey puck on ice, ice is relatively frictionless, and then you no longer have to exert a force on it to keep it moving. That would be no forces applied. It's applied initially to get it moving, but then afterwards it isn't. That's not work. When a force causes a motion to move, it has to move some distance. If it doesn't move some distance, no work was actually done. You can push and push and push on a stationary wall all day long and break a sweat. It doesn't mean that you've done any mechanical work if you haven't moved the wall. And the force and the motion must be parallel. They must be going in the same direction. If they're not going in the same direction, then no work is done. They could be going in opposite directions or the same direction, but it has to be parallel. Okay, so when are you doing work and when are you not doing work? So here's a few examples. So if you are lifting up a baby, okay, you're lifting up something against gravity. So you have to look at the force and the velocity, like where you're going, because that's where your distance is. So you have your baby. Okay, so if you're lifting the baby, your force is directed up and you're moving upward. So if your force and you're moving some distance in the same direction, parallel, then you are definitely doing work. So work is done. If you're carrying a bag, so to carry a bag, what happens is your force is directed upwards, but you're moving in a direction that is perpendicular to the force. This is not work. Okay, not work. So anytime you are carrying something, so carrying is never work, because you don't have those two things that are parallel, they're perpendicular. If you're pulling a wagon, well, depends on, if you're pulling a wagon, typically, like if you're pulling a wagon down the sidewalk, your force might be directed at an angle, right? So your force is this way and you're going this way. But what happens here is, because your force is directed at an angle, right, we break it up. So we'd have like a tension force maybe. So you'd have tension in the Y and you'd have tension in the X, because tension in the X and the displacement are going in the same direction. This is work. It's not doing any work vertically, it's only doing work horizontally, but that's work. So they're going in the same direction. Okay, so let's talk about signage, because that matters too. I could turn the page. Okay, so signs. So if you want positive work, then the force and the motion must be going in the same direction. So let's say they're both going north. Okay, your force and your motion are going north, then you are doing positive work. Okay, so so here, let's actually draw that. So if your force is directed that way, and let's say that's north, and your velocity, which is what derives your displacement, is going in the same direction, then you're doing positive work. If force and motion are going parallel to each other but in opposite directions, then you still have work, but now it's negative. Okay, so this would be like if you had friction. So if your car is moving this way but you hit the brakes, then the friction force is directed in the opposite direction. So think about, this is east and this is west, right? East is positive, west is negative. So you have negative work being done, okay? So just so you know though, friction always does negative work. Okay. Now, there's this thing called network, and you're going to see this in your homework. You have network. Network and total work are the same thing. So you'll see both terms, but they're the same exact thing. But this is for like if you have more than one force doing work. Like when you did net forces, you'd have to calculate all the forces in one plane. This is what you would do if you have more than one force in the same plane. You'd have to calculate net work, just like you did net force. Positive net work means that the object is speeding up. Negative net work means the object is slowing down, like up here where you hit the brakes, okay? And zero net work means that an object is either stationary, like you pushing on the wall all day and it not moving, or an object is moving at constant velocity. So if it's moving at constant velocity, there's no net force. The net force is zero. So if the net force is zero, then the work also has to be zero, okay? Now, let's talk about situational work. So which one of these situations is more work? So first situation, if you lift an object straight up for 2 meters, so the object obviously has some mass, okay? If it didn't have mass, it wouldn't be a thing. But it has some mass and you lift it up 2 meters. Or you're going to use a ramp and you're also going to reach a height of 2 meters, but you're going to use a ramp to ramp it up, okay? Which one is doing more work? It's a trick question, okay? They are the same, okay? Why are they the same? Well, they have different forces, okay, or their forces are directed over different distances in the parallel sense, but they're still doing the same amount of work. So in this one, your force is working against FGX, which is a component of gravity. And the hypotenuse of this is definitely longer than the opposite side. So you have in the A portion, you have more force that you're directing over a short distance. Okay? So more force over less distance. But on the ramp, you're going through the hypotenuse, which is a greater distance, but the force is a component of gravity. A component of gravity means it's going to be less than gravity. This one, you're working straight against gravity. So this one, you have less force, but you have it over a longer distance. Okay? Either way, you're doing the same amount of work. Okay? Okay, so that's all for work. Let's talk about power. Power is relatively simple. It's the rate at which work is done. When you see rate, you have to think over time. So it's literally work divided by time. Now, power is measured in a weird unit. Power is measured in watts. And I know it's weird because we use W for work. We're also going to use W for watts. But watts is a unit. Work is an actual factor in the problem. Work is still measured in joules. Time is measured in seconds, like it has been for the duration of the first semester. Okay? So here's an example problem. You have a 25 kilogram stroller. It's pushed with a 90-degree force. Speaking is hard. A 25 kilogram stroller is pushed with a 90 Newton force at 35 degrees above the horizontal for 100 meters. Okay. So what's happening? I need to draw a little picture and describe what's happening, right? So here's my stroller. It's 25 kilograms. I'm pushing it, so I'm pushing it down and maybe to the right. I don't know, to the left, to the right. I'm going to push it down and to the right. So my force applied is down and to the right. So I have to break that up. So I have, FAX and FAY. I know this thing has mass, so gravity is affecting it, so it has Fg. It's on a surface because I don't generally push strollers on clouds. They have to be on a sidewalk of some sort. So I have a normal force. And it's giving me a mu. A mu means I have friction. So friction must be directed in the opposite direction of my force applied, in the x direction along the sidewalk. So there we go. Now it's asking for work done by each force. That means how much work is done by the force moving the stroller to the right, and how much work is done on friction. Okay, so for part A, work is equal to force times distance, right? Well, the FAX, because it's done at an angle, but it's still along the horizontal, in this case, I'm going to use work is FD cosine theta. Okay? So my force is 90 newtons. My displacement is 100 meters. And I'm directing it over, a 35-degree angle, so cosine 35. So then my work done on to push the stroller, so this is for the push. My work done on this push, stick that in a calculator. Make sure your calculator is in degree mode. Okay, so it's 7,372 joules. So that's how much work is done to push the stroller. But I also need to know how much work is done by friction. Okay? So work done by friction, so that's friction times displacement. Well, friction is equal to mu times normal. I haven't calculated my normal force yet. Well, let's see. So my normal is going to be equal to the sum of my gravitational and my FAY. So that means I'm going to do mu times FG plus FAY times displacement. Well, mu times Fg is mg plus Fay would be the force applied sine theta, and then multiply that by d. So it's a mouthful, but we can do it. So 0.21 times, let's see, our mass is 25. I'm going to put this in brackets. 25 times 9.81 plus my force applied, which is 90, sine theta, which is 35. And all of that also times your displacement, which is 100. Believe it or not, you can stick that all in your calculator. So 0.21 times, let's see, open parentheses, 25 times 9.81 plus 90 sine 35 times 100. All right, and you get that. However, I forgot one crucial thing. If it's friction, it's moving to the left. So this is negative for all of these. So your answer is negative 6,234 joules, because friction is negative. Okay, so that's how much work is done by each force. I want to know the net work. In order to know the net work, I have to know the net force. The net force is the sum of the forces in the x direction, okay? So this is going to be my net force. So I'm going to say this is positive, but this is negative. So it's going to be Fax minus friction. So Fax is just Fa cosine theta. Friction, we determined friction to be basically this without the displacement. So mu times gravitational plus Fay. So your net force is 90 cosine 35 minus 0.21 times, put that in brackets, times 25 times 9.81 plus 90 sine 35. Okay, so let me get my calculator right quick here. Let's see, let me scooch this guy up. Okay, so again, make sure your calculator is in degree mode. So 90 cosine 35, close parentheses for sure, minus 0.25 times, open parentheses, 25 times 9.81, plus 90 sine 35, close parentheses, close parentheses. There we go. Is my calculator not in degree mode? No, it is. And then I must have pressed something wrong. Let's see. I guess not. Okay, that makes more sense. Okay, so that should be 11.4. I'm going to type it in again. 90 cosine 35. Look at that. I'm a human. I screwed something up. Minus 0.2. Oh, what is my mu? It's 0.21. Oops. Okay, there we go. That's what I did wrong. 0.21 times, oh, parentheses, 25 times 9.81 plus 90 sine 35. Okay, that's better. Okay, so it's about positive 11.4 newtons. Okay, so that's my net force. Okay, so my net work, because that's what I'm asking for in part B, my net work, right? So my net work is force in the x, or my net force in the x direction, right? Times displacement. Well, my net force is 11.4 newtons times my displacement, which is 100 meters. So it's just going to be I'm just going to times 100. So 1138, which in this case, since I didn't round enough, 1140 joules, because work is in joules. All right, and then part C asks, what's the total output? And it says net output in 32 seconds, which means I have to use net work for that. So power is equal to work over time. My work is 1140. The time is 32 seconds. So then it's just 1140 divided by 32 seconds, and I get about 35.6. And this is watts. Okay, so that's one full example problem, similar to stuff that you'll see in your homework. I wanted to do another example problem, but because some of your homework involves things that are just lifting, where you're just working against gravity. So I wanted to do an example problem. Sorry, obviously I'm at school. Okay, I'm gonna do an example problem with one of the things that's being lifted. So if I had a construction machine, I guess a crane, that's lifting a beam with a mass of 800 kilograms over a distance of 20 meters, so a height of 20 meters in 60 seconds, I want to know what's the work and then what's the power. Okay, so what do we have? We have a machine, or beam, sorry, that's 800 kilograms. And it's being lifted, so I'm going to call this, I don't know, you want to call it force applied or tension? Be my guest. I'm going to call it force applied for funsies. And my force applied is going to be exactly opposite of my gravity, okay? And let's assume there's no air resistance, okay? And we can assume it's, oh, whoops, I should probably say that, at constant velocity. Okay, let's assume it's at constant velocity. Okay, so my force applied is going to be equal to, what's the work done, let's say, by the machine. And I want to know what's the power output of the machine. Okay, so because if I wanted to know net work, it would be 0. If it's going constant velocity, your net work is 0. If your net work is 0, then your net power is 0. Okay, but I want to know the work done specifically by the machine and the power output of the machine. Okay, not net, just the machine. So just the machine, I'm looking at just this. Well, if I have no net force, right, then my net force in the y is equal to Fa plus Fg, which is 0, which means that Fa would equal Fg in magnitude, which is mg, which is 800 times 9.81. So then my force applied would be 7,848 newtons. Well, my work is equal to force times distance. Now, this is moving in the vertical. So there's two ways to do this. Either you calculate your force applied separately like I did, or this is force of gravity that it's working against because it's lifting. So you can literally call this mgd. And you can plug it in there. So then it'd be 800 times 9.81 times your displacement, which is 20. And this is a little more efficient than calculating the force first and then plugging it into F times D, right? So then that would just simply be 800 times 9.81 times 20. So that's a lot of work, right? So 150, I'm just going to say 157,000 joules. So that's how much work is done. Okay. Now for part for part B, I want to know what's the power output of the machine. So power is just work over time. I already have the work. It's 157,000. And I'm doing this over 60 seconds. Okay. So I get about 2,117 watts. Okay, so that's the power output of the machine. Okay, if I hadn't done the work first, if it only asked me what's the power output of the machine, well, the power output of the machine would just be power equals, in terms of lifting, it's going to be Fg times D over time, which would equal mgd over time. So you got to remember, this is for lifting. Okay, and it's not for net power or net work. This is for the work done just by the thing that is doing the lifting. Okay, so I want you to be careful when you do your homework. Pay attention to words like parallel and lifting so that you know exactly which of these things to employ while you're doing your work. Also look for the words net and total and understand what they mean as well. Okay? Good luck. I hope you do a good job, and I hope to see you soon. Stay healthy.